In 1971, Ronald Graham and Harry Pollak were working on a theoretical problem in network communications. At the time, they were researchers at Bell Labs, a preeminent commercial research institute responsible for many of the computer technologies ubiquitous today. It was also the R&D branch of the Bell Systems, a group of companies in charge of most of the local telephone services in the United States and Canada. The problem was this. Suppose we had a network of n nodes where every pair of nodes is connected by a wire. The nodes communicate with one another over several rounds. In each round, a node can be in exactly one of three states: asleep, sending, or receiving. Each node in the sending state sends a message to each node in the receiving state. Our goal is to send or receive some message over every wire exactly once, using the fewest number of rounds. We can translate the problem into graph theory. Graphs consist of vertices and edges. Here, the vertices are the nodes in the network, which we will label 1 through n, and the edges are the wires between the nodes. A graph where every pair of vertices is connected by an edge is known as a complete graph and is denoted by k sub n. Consider a round of communication and pay attention only to the sending and receiving vertices and the edges between them. Notice that messages are sent between every pair of sender and receiver and never between pairs of senders or pairs of receivers. Thus, when we color the senders red and the receivers blue, an edge must have endpoints of different colors. Graphs which can be thusly colored are known as bipartite graphs. Further, since every red vertex is connected to every blue vertex, every round is a complete bipartite subgraph in the original graph. Asking for the fewest number of rounds so that a message is transported on every wire is equivalent to asking for a complete graph to be decomposed into the fewest number of complete bipartite graphs. In particular, every edge of the complete graph should appear exactly once in a complete bipartite graph component. Here is a possible way to decompose K5 into 4 complete bipartite graphs. Can we do better? More generally, can we decompose k sub n into fewer than n-1 complete bipartite graphs?